Hi there, this is the second part of the development of a power monitor for DC. If you recall, I started off with this diagram outlining what I was looking for in principle, measuring volts and amps, and then calculating power, capacity, energy, and possible additional statistics, while recording the measurements somehow, for example, to graph them. I also wanted the power monitor to be able to run off mains to allow continuous long-time measurement over many hours or days. During part 1, I refined the preliminary design to look like this. The dedicated power monitoring chip INA219 is handling the input by measuring the voltage drop over a shunt resistor and the bus voltage over the load. From these values, the chip calculates current and power and makes all this available over the I2C bus. The processor handling the I2C is a Raspberry Pi Zero with built-in Wi-Fi, and at the end of part 1 I was able to read those 4 values successfully from the chip. The other functions remain to be implemented, as does the recording, which will now take place on the Raspberry Pi itself, rather than a connected PC. This has the advantage that during long-term measuring and recording for many hours, no PC connection is needed, a definite plus. But I want to be able to see the measurements and possibly change ranges, so in today's installment I'm going to add an LCD display and a couple of buttons to the Raspberry Pi to do just that. But before that, there's one thing I missed explaining in part 1, and that is how to prepare the Raspberry Pi. Because the stuff in this and the following installments depend on this, let's go over it briefly. Starting with a fresh install of Raspbian Stretch in part 1 and letting it do its self-update to the latest version, I used the Raspberry Pi configuration menu to enable SSH, VNC and I2C. Because I normally use VNC to remote desktop into the Pi, and if there is no physical monitor attached, the remote desktop defaults to a tiny 640 by 480 resolution, so best change the resolution to a decent size now. Next, set up Wi-Fi, and then you can disconnect the physical monitor, keyboard and mouse and use remote desktop instead. Part 1 only needs I2C, and for that you need the Adafruit GPIO library. Part 2 needs a few additional libraries, so let's have a quick look at those. It has been a while since I last looked at the Adafruit libraries for the Raspberry Pi, and so I was somewhat surprised to find them gone, or at least greatly reorganized. The problem is that there are still tons of examples and tutorials on the web that rely on the old libraries, so the picture is a little confusing to say the least. You have essentially a choice to go with the legacy libraries that you can still find, but they are stripped of installation instructions except what you find in those tutorials, or go with the new stuff. I thought for this project I give the new stuff a try. The first thing we need is of course access to the GPIO or general purpose IO, which also includes the I2C interface. The installation instructions are clear enough. In an up-to-date Raspbian Stretch, you find that the first couple of lines are unnecessary because everything is already installed. For this and the following installs, the video is sped up to save time. Also, I only plan to use Python 3, so any commands where this is not explicit I changed accordingly. Onto the LCD panel. It turns out that this library is now depreciated and unsupported, and you have to use CircuitPython libraries for the latest and greatest. CircuitPython is essentially a subset of Python that can run on microcontrollers much less powerful than the Raspberry Pi, so these libraries can be used on a Raspberry Pi without problems. You just need a bit of code that maps the CircuitPython settings to what the Raspberry Pi offers. This piece of code is called Ada Blinker. And this is how you install it. So let's do that. This lengthy process downloads and sets up the CircuitPython stuff for the processor and I/O chips on a Raspberry Pi. And now we can install the Adafruit CircuitPython char LCD module. The instructions are here. It is quite an involved process as it automatically installs a few dependencies. With that completed successfully, everything needed to talk to the INA219, the LCD, and use digital I/O for buttons and the like is set up and ready to go. The modified wiring diagram looks like this. The INA219 wiring and the I2C connection to the GPIO of the Raspberry Pi is exactly the same as in part 1. The LCD panel is one of those ubiquitous 1602A sets that can be used with a 4 or 8-bit wide data bus. In this setup, it uses only the upper 4 bits. The other 2 lines driven by the Raspberry Pi are the pin 4 register select and pin 6 the enable signal. Pin 5, the read-write signal, is permanently connected to ground corresponding to write mode. The 5V power for the display chip comes in at pin 1 and 2, while the LEDs for the backlights are powered at pin 15 and 16 and have a 220 ohm resistor in series. A 10K trim pot provides the adjustable voltage to set the display contrast. I picked 4 unused GPIO ports to connect 4 push buttons, and I configured the GPIO pins for these buttons to use internal pull-up resistors, and so the buttons can simply be wired to connect the relevant pin to ground. I added 1 GPIO pin to be configured as output, and for now this is simply driving an LED. Eventually I will probably connect a relay to allow the software to disconnect a battery, for example, when discharging. Compared to part 1, I slightly reconfigured the test circuit on the left to make it more clear. I added 2 meters to be able to compare the readings with the values from the INA219. The other change is that the slightly higher resistor allows tests with a higher voltage. Here's my wired up prototype that matches the diagram, with the LCD, buttons and the LED all connected to the Raspberry Pi Zero. On the bottom left you will recognize the little INA219 board from part 1. You will also notice that the LCD actually displays proper values and they are updated as well. I can tell you that this wasn't quite as straightforward as I had hoped. The basic setup for talking to the LCD panel is easy enough, as you can see here. We define which GPIO pins drive which pins on the LCD panel and use that and the number of rows and columns to instantiate the LCD object from the character LCD mono class. That class takes care of the slightly convoluted method required to get characters and commands across the 4-bit interface to the LCD controller. The Raspberry Pi writes some data and pulses the enable line for the display and hopes that the LCD controller picks that up in time. Because that LCD controller chip isn't very fast, the Raspberry Pi artificially delays the next write, so writing characters to the LCD isn't very fast. All this is done invisibly under the hood, so users can ignore all that and start using the LCD like here. First we clear the whole panel of anything that may still be shown there. Then we write a message, "Hello world," and sleep for a few seconds to have time to admire it on the LCD. This is followed by another short message, "OK." Next I clear the screen again, print a message that we are about to turn the cursor on visibly, and then do that by setting the properties for showing the cursor and making it blink. And then I position it at column 8 in the second row. The numbers start at 0, so the 8th column is really the 9th position on the line. Similar, the first line is actually line 0. I hope you're not getting too confused by that. Now I write another message, hi, followed by another message, there. Let's see it in action. Hello world appears as you expect. Whoa, what's that? Hello world? The OK message simply overwrote the first part of hello world instead of following behind. That's definitely not OK. Now show cursor is displayed and the cursor is blinking in the desired position, column 8, row 1. That's good. But hi is not printed where the cursor is. It starts again at the first column, first row. At least it took the cursor with it. But there is again ignoring the cursor and starts from the beginning. The inability to print a message where you want it by setting an explicit cursor position, and that you can't send messages one by one where each new one is printed behind the previous one, makes this whole library pretty useless for serious programming. Of course you can send always messages as complete strings of 2 × 16 characters with a new line character in between, which means writing always both complete rows even when updating just one character. That gives you full flexibility, but the performance penalty is terrible. This behavior, by the way, is not the problem of the LCD controller, but the class, and it's apparently by design and not considered a bug. Of course we can fix this. I could make my own LCD driver, warts and all, or borrow this private function from deep within the existing class. A class method starting with an underscore means by convention this is private to the class and subject to change at any time, so me calling it directly is very naughty. Please don't tell anyone. However, it allows me to write text to the LCD without the unwanted interference happening in the original message call. As you can see, I have simply replaced all uses of the message method with my clutch. Here's a test run of this version. Hello world, followed properly by OK, because unlike the original, my function does not override the cursor position and always set it to 0, 0. Now show cursor is displayed at the beginning. After setting the new position, the cursor is blinking at the desired position, column 8, row 1. And that's exactly where hi is printed, as you would expect without touching any other text on the display. And there is using the last cursor position and follows the hi as expected. Until CircuitPython changes their mind on the way the message method works in the original, at least for now, I'm going to use my workaround to make the LCD display behave the way I want it. There are a few other quirks of the LCD panel itself which I want to mention because it does drive the user interface design, but for brevity let me just use this summary diagram instead of many code examples. When you write to the panel, you're actually writing into the memory managed by the LCD controller, and the cursor location is simply a pointer into this memory. The memory is quite a bit larger than necessary for this 2x16 module, which is simply because the controller is also used for larger displays with more rows or longer columns. In this display, only the addresses from 0 to F are visible in the first row, and hex 28 to 37 in the second row, because the way the library computes the memory address from row and column numbers, this is equivalent to 2 rows each with 0 to 39 columns, of which only 0 to 15 are visible. What are the effects of all this? If you write a text that is longer than 16 characters on the first row, it doesn't automatically wrap to the second row. Instead, the text lands in the invisible part to the right of the LCD. Only after this part is full does the text wrap into the second line. The same happens if you write a really long text in the second line. After the first 16 characters, it goes into the invisible space, and once that is full, it wraps back into the first line. So from a point of writing text, the display really behaves as a block of 80 characters, of which only 16, 2 times 16 are visible, the first 16 starting at 0, the other at hex 28 or decimal 40. Things are different when you use the scroll function available in the controller. You can tell the controller to shift the content of the memory one character to the right or left. Now the controller is not simply rotating the whole block of 80 characters, as you might expect. Instead, the controller scrolls the memory areas corresponding to the two lines simultaneously but separately. When scrolling right, for example, all characters in row 0, including the invisible ones, move one to the right, and what was in position 39 is inserted into position 0. The same happens at the same time for the second row. No text is lost during scrolling, and no text ever moves from one line to the other. Since scrolling always affects both lines, you can't have one line displaying fixed text and the other a rolling banner like you see on TV for breaking news. Also, a message scrolled right on the first line disappears instead of surfacing on the left on the second line, as you would expect. But keep scrolling for longer and a disappeared message suddenly reappears on the left of the same line it was on once it has scrolled through the invisible character portion. Compared to the LCD stuff, testing buttons and turning on relays, or standing in LEDs in this case, is fairly straightforward, as you can see. The only slight complication is the negative logic needed. Because of the pull-up resistors, the ports reads true when the button is not pressed and false when the pressed button connects the pin to ground. The other thing to note is that I use separate booleans for each button to implement a simple edge detection to enable the program to detect when a button is pressed and when it's released. My main concern here is contact bouncing, because mechanical switches do that, and it may cause the program to detect multiple button presses for each physical one. To help detecting this, the program prints out an incrementing event number for each button. If you would just print button pressed, button released messages, they all look alike on the screen, and you can't spot if your press triggered 1 or 2 printouts. Another thing to mention is that I put a simple toggle mechanism for the future relay output in the button 4 pressed code. So with a press, we should be able to turn on the LED, and it should stay on even if we let go of the button until another press of the same button is detected. I also use the LED status to indicate whether a slow or faster polling method is used. When the LED is on, we check the buttons 10 times per second, but when off 100 times per second. I want to see if the speed causes bouncing issues to appear, meaning the program would see multiple button presses for each physical one. Let's see how this works. Pressing button 1. Pressing button 4, the LED comes on. Pressing button 4 again. So far we had one event on button 1 and 2 on button 4, which is what it should be. Pressing button 1 and holding it and releasing works as it should. 4 quick pushes on button 1 should get us to event number 6, and it did. Now pressing button 4 to turn the LED back on and selecting the slow scan. Doing another 4 fast presses on button 1 should get us to event number 10. No problem. And finally, putting it all together, this is the code that I'm currently running on the Raspberry Pi. Although it looks kind of complicated and messy, you should by now be able to recognize most of it, because it's really just putting the previous programs for INA 219 setup and reading, LCD writing, and buttons reading together. The main purpose of this program is to continuously read values from the INA 219 chip and display them on the LCD. The layout looks like this, and the X's are just placeholders that will be overwritten with actual values later. I want to use the program to test the accuracy of the INA219, and therefore I want to be able to quickly change some configuration parameters using the buttons. But to be able to see on the display what configuration is active, I came up with this method. The three parameters are the shunt voltage range, the bus voltage range, and the averaging rate. All are independent from each other and can be used in any combination. Because there's just space for one additional character on the display, all three parameter settings are mapped into a single character as shown here. So for example, if the SV range were 1, which is actually 80 millivolts, the bus voltage range 16 volts, and the averaging rate more than one sample, the character would be a 5. If bus voltage range were changed to 32 volts, it would become a lowercase f. This is just a temporary way for me to know what is selected. This section here reads the INA219 and updates the relevant portions on the display, but only if the value has changed since the last time to reduce the number of writes to the relatively slow LCD. This is implemented by comparing the newly read value with an old value and at the end setting the old value to the new value for the next cycle. The bus volts and the shunt volt values are also checked for overflow or rather reaching their maximum allowed value. Button 1 toggles between 16 volts and 32 volts bus voltage range. Every press on button 2 increases the shunt voltage range until the maximum of 320 millivolts is reached. Button 3 decreases the shunt voltage range until it's back down to 40 millivolts. Button 4 toggles between two averaging settings, namely 1, which means no averaging, and 8 samples to average. I just want to see what difference averaging makes. And here's the LED standing in for future relay, and it's set to light if an overflow is detected. Since part 1, there are a few changes on the handling of the INA219 that I want to point out. During testing I found an error in the calibration value for the 40 millivolt range, so this here is the correct value. The same structure now also includes the maximum shunt voltages to simplify the range checking. Instead of 4 read functions for bus voltage, shunt voltage, current and power, there is now just one, and the values are kept in a tuple called VAPS, standing for volt, amperes, power and shunt. The bus voltage register includes a bit that indicates whether the INA219 math processing for current and power has overflowed. This bit is now checked, and if it's set, the power and current values are set to invalid. The test load is the same LED as before, but with higher resistor, so the voltage is now close to 16 volts. If I increase the voltage slowly, the bus voltage display freezes at 16 volts because we have exceeded the 16 volt bus voltage range and the overflow LED comes on. But I can use button 1 to set it to 32 volts and increase the voltage further. Note that the overflow LED went out again and the configuration character in the first row has changed from 0 to lowercase a to show that 32 volts range is now selected while the shunt voltage range is still 40 millivolts. I short circuit the LED, which raises the current to about 55 milliamps and 5.5 millivolt shunt voltage. Let's increase the current until 40 millivolts are exceeded. Here we are. The overflow LED is on again. I can now use button 2 to select the next higher range of 80 millivolts, which turns off the overflow LED and changes the configuration character to lowercase b, as now both 32 volts bus voltage and 80 millivolt shunt voltage range are still active. I used this setup to do some extensive testing of the accuracy of the bus voltage and current displayed. As those runs are similar to what you just have seen and very repetitive and boring, I skip showing the process and go straight to the interesting results. The first column shows the bus voltage as measured by my benchtop multimeter. I stopped at 24 volts because the INA 2119 can't handle more than 26 volts. The next two columns are the values displayed on the LCD screen with a 16 volts or 32 volts bus voltage range selected. The following two columns are the measurement error in percent for both settings, and the graph plots these against the bus voltage value. The result is not what I was expecting. Both ranges show an almost exponential increase in the error the lower the voltage becomes. Even more strangely, the problem is worse for the 16 volt range, when you would expect that range to perform better for smaller voltages. It is clear that whatever causes it, it is amplified by the lower range setting, or to put it in another way, doubling the range halves the error. Since I'm not using the INA 219 Python library, I made sure the error isn't caused by that. The test program of part 1 used the latest INA 219 library, and it shows the same values. One thing is for sure, there's absolutely no point to ever selecting the 16 volt range. This accuracy is of course relative to my 6-digit benchtop multimeter, but for me that is definitely good enough. Is it worthwhile to develop a software compensation for the voltages below 3 volts? I'm not sure. In addition of doing this, it would mean one has to calculate power as well, because the chip would of course use the uncorrected voltage. Since 16 volts and 32 volt ranges have the same resolution of 4 millivolts, there is no point for ever selecting the 16 volt range, so that function can be removed from the program in the future. Here's a similar set of measurements and graphs for current, but since there are 4 current ranges, everything is a bit more evolved. Because of the large overall range from 1 milliamp to 3.1 amps, the second plot here gives a zoomed in view of the range of 0 to 500 milliamps out of the overall range here. The accuracy of the current is excellent and generally well within 0.5%, again relative to the comparing instruments, which is in this case a BM235 multimeter. The zigzaggy plot is caused by single-digit differences when the actual current is somewhere between what the least significant digit of the current display can show. Take that prominent peak here at the 160 millivolt range. For example, the error is 0.63%, but if you check the values here, you see that the displayed value was 0.159 when the actual one was 0.158, which is just one digit different. I am very pleased with the current accuracy in all the ranges. Even though the highest current range is as accurate as the lowest one, there's still a case for having different ranges in the program, because for current the resolution of the 4 ranges differs. What it means actually is that the LCD display format for the lower ranges should probably change to use milliamps instead of amps to have space for more digits. A quick word on the Raspberry Pi boot and shutdown sequence. If you apply power to the Raspberry Pi board, the operating system, in this case Raspbian, starts, and it's easy to configure it in such a way that it will automatically start the Powermon application. Once you don't need Powermon anymore, it's important not to simply turn power off. Raspbian needs to be properly shut down to have time to orderly terminate all running services, flush all pending writes to disk, and close all open files. This is particularly important if Powermon was doing recording. So one of the user interface functions of Powermon has to be a way to issue an off command. I don't know yet what that might be, a menu option or a special button combination or something. Obvious options. Once that has been detected by Powermon, it can do its own housekeeping, saving files and so on, and then issue a shutdown and power off command to the operating system, which is easy to do in Python. The operating system goes through its housekeeping task as explained and then powers the Raspberry Pi off. Once that state has been reached, it is safe to unplug or turn off power of the Raspberry Pi. In fact, you have to do this to be able to reboot again. The problem is, as a user, you don't know when that state has been reached. If the Raspberry Pi has no screen attached and you can't see the onboard LEDs either, and user programs like Powermon are already dead and can't display anything. When playing with the button test program I showed you earlier, I noticed that if the temporary relay LED controlled by the button 4 was left on during shutdown, it will automatically go off when the Raspberry Pi has reached the power off state. So putting an LED on the front panel driven by a GPIO output pin would be a good way to indicate when it's safe to remove power. But rather than adding a dedicated LED for this purpose, how about using the LCD backlight for that purpose? The display module's datasheet is silent about the power consumption of the backlight. It only states that it's a white LED. It doesn't even state if a current limiting resistor is needed or not. I did add one of 220 ohms just in case. So let's investigate if you can drive it from the GPIO. I first ran the Powermon program to display something, then I killed it, which leaves text on the display, and then I started button test 1 to be able to control the relay LED through button 4. Connected directly to 5 volts through a 220 ohm resistor, the backlight draws about 7.67 milliamps. Instead of to the 5 volt rail, the backlight 220 ohm resistor is now connected to the output driven by button 4. Pressing it turns it on, drawing just below 2 milliamps, but the backlight is too dim to be usable. That is because the GPIO delivers only 3.3 volts, not 5 volts. Bypassing the 220 ohm resistor boosts the backlight to a usable level, needing the GPIO to provide 4.74 milliamps, which is within the allowed range. Watch what happens to the LCD when I issue a shutdown command through a VNC remote desktop session. It works great, so this method is what I'm going to use to indicate the shutdown state. Well, that's it for this installment. The next steps are applying the lessons learned from this part, namely the backlight wiring, removal of the useless 16 volt bus range, and changing the current display format to show a higher resolution for low currents. Then I want to start developing a prototype of the user interface and menus, and think about the power supply and how to incorporate a relay to allow the Pi to turn off charging or discharging of batteries. I am considering to move the 0.1 ohm shunt resistor away from the Adafruit board for a couple of reasons. The board looks a little flimsy to run 3 amps through it for extended times, and having the shunt separate would allow using different shunts for more current ranges. It also would allow adding an interference filter as mentioned in the INA 219 datasheet, and possibly over voltage protection. Like for part 1, I've put the software programs and the wiring diagram shown in this video into my GitHub page. The link is also in the description of this video. Please leave comments below, and if you haven't done so already, consider subscribing so you don't miss the next parts. Thanks for watching.